In this lecture, we are going to describe kinematics using rotating and translating reference frames. Okay, so this theory, after we're done doing it, is going to be followed up with an example. So, rotating and translating reference frames are, the setup for them is as follows. I have a frame, I'm going to call this frame A. I have a point O. O is fixed in A. I have another frame, I'm going to call this frame B. I have a point Q that's fixed in B. Q is fixed in B. I have the vector from O to Q, which is the position of Q relative to O, and then I have an arbitrary point out here, P. P is an arbitrary point. Now, we're going to decompose the vector from O to P. So let's draw the vector from O to P. There's the vector from O to P. That's the position of P relative to O. We're going to decompose that into the vector from O to Q plus the vector from Q to P. So that's the position of P relative to Q. Now here are the two stipulations that are going to be made when doing this this derivation. The first one is that observations of the motion of Q are made in reference frame A. 2 is that observations of the motion of P are made in reference frame B. So what we're saying is that we cannot directly see how point P changes in reference frame A. We actually can see how P changes in reference frame B, and since Q is fixed in reference frame B, we're going to measure all our distances from point Q. We can see how Q changes directly in reference frame A, however, and Q is measured relative to O, and O is fixed in reference frame A. So now, here's the setup. The position of P relative to O is equal to the position of Q relative to O plus the position of P relative to Q. So we want the velocity and acceleration of P as viewed by an observer in reference frame A. So we know that the velocity of point P in reference frame A is equal to the rate of change in reference frame A of the position of P relative to O. That's equal to the rate of change in reference frame A of the position of Q relative to O plus the position of P relative to Q. Now, if we break that up further, we get that the velocity of point P in A is equal to the rate of change in A of the position of Q relative to O plus the rate of change in A of the position of P relative to Q. But remember, I said that observations of the motion of point Q are made directly in reference frame A, so there's not going to be any transport when we're looking at the rate of change of point of the position of Q relative to O. We're directly going to get the velocity of point Q in reference frame A. But observations of how P changes are being made in reference frame B, and we want the rate of change in reference frame A. So that's going to introduce a transport. The transport being the rate of change in B of the position of P relative to Q, plus the angular velocity of B in A crossed with the position of P relative to Q. Now that is going to equal the velocity of point Q in A plus the velocity of point P in B plus the angular velocity of B in A crossed with the position of P relative to Q. So that gives us the velocity of point P in reference frame A. It's decomposed into the velocity of point Q in reference frame A plus the fact that observations of the motion of P are being made in reference frame B, and we want the rate of change in reference frame A. Therefore, we have to apply the transport theorem on the second part of the vector, which is the transport theorem applied to RP relative to Q. We need to transport from reference frame B to reference frame A. So now we're going to do the acceleration. So next, the acceleration of point P in A is equal to d dt in A of the velocity of P in A. But that is equal to d dt in A of the velocity of point Q in A plus the velocity of point P in B plus the angular velocity of B in A crossed with the position of P relative to Q. And that's just using the velocity that I just computed. So now let's compute this rate of change. This rate of change is equal to d dt in A of the velocity of Q in A plus d dt in A of the velocity of P in B plus the angular velocity of B in A crossed with RP relative to Q. Now, remember that motion of point Q, according to my stipulations, motion of point Q is observed directly in reference frame A. So this is going to be the acceleration of Q in reference frame A. There's no transport required on the first term. But the second part is going to require another transport. I've got d dt in A of the velocity of P in B plus d dt in A of the angular velocity of B in A crossed with RP relative to Q. So now let's do the transport. We know that observation of the motion of point P is being made in reference frame B. So this gives me the acceleration of Q in A plus, now I'm going to apply the transport theorem to the velocity of point P in B. That's equal to d dt in B of the velocity of point P in B plus the angular velocity of B in A crossed with the velocity of point P in B. And then I have the last term here, which is d dt in A of the angular velocity of B in A crossed with the position of P relative to Q. Now, we know that results in the acceleration of P in A is equal to the acceleration of Q in A plus, now if we look at the second term, d dt in B of the velocity of P in B is equal to the acceleration of P in reference frame B. And then I have plus omega BA crossed with the velocity of point P in B. And now I have the rate of change of this last term. So the rate of change of this last term, if I look at d dt in A of omega BA crossed with RP relative to Q, that gives me d dt in A of omega BA crossed with RP relative to Q plus omega BA crossed with d dt in A of RP relative to Q. But remember that the rate of change of the angular velocity between two reference frames in either of the two reference frames is defined as the angular acceleration of that reference frame. So I get the acceleration of Q in A plus the acceleration of P in B plus the angular velocity of B in A crossed with VP in B, and then I get plus, now I've got the angular acceleration of B in A crossed with RP relative to Q, and that's the term that's the d dt in A of omega BA crossed with RP relative to Q, and then I get plus omega BA crossed with d dt in A of RP relative to Q. But remember that observations of the motion of point P are made in reference frame B. So this becomes the acceleration of point Q in A plus the acceleration of point P in B plus the angular velocity of B in A crossed with VP in B plus the angular velocity, plus the angular acceleration of B in A crossed with RP relative to Q, and then I get plus this last term. So if I do this last term on its own line, I get the angular velocity of B in A crossed with, now if I apply the transport theorem to RP relative to Q, I get d dt in B of RP relative to Q plus the angular velocity of B in A crossed with RP relative to Q. So if I simplify that even further, I get the acceleration of point P in A is equal to the acceleration of point Q in A plus the acceleration of point P in B, and then I have plus omega BA crossed with the velocity of point P in B, which is that term, plus the angular acceleration of B in A crossed with RP relative to Q, and then I have plus omega BA crossed with, now if you look at the term here, I've got d dt in B of RP relative to Q, but d dt in B of RP relative to Q is equal to the velocity of point P in B. And then I have the last term, which is plus omega BA crossed with omega BA crossed with RP relative to Q, which gives me that the acceleration of point P in A is equal to the acceleration of point Q in A plus the acceleration of point P in B. And now you'll see here that I have two of these omega BAs crossed with VP and B. So I get plus 2 omega BA crossed with VP in B plus the angular acceleration of B in A crossed with RP relative to Q. And then I've got plus omega BA crossed with omega BA crossed with RP relative to Q. So I get 5 terms when I'm all done. And you can see that when we do this, we've decomposed the motion into motion of point Q, where the observations are taking place directly in reference frame A, plus terms that involve the motion of point P transported from reference frame B to reference frame A. This last result is actually what's often called the 5-term acceleration formula using a rotating and translating frame. And it shows you that there are different constituent parts to what's happening when you actually transport from one frame to the other. For example, the last term in here, this omega BA crossed with omega BA crossed with RP relative to Q, is often what's called the centripetal acceleration. The alpha BA crossed with RP relative to Q is what's called the Euler acceleration. And the 2 omega BA crossed with VP and B is what's often called the Coriolis acceleration. Now, this is the theory behind this. When we actually apply this, we're going to go back and do this one derivative at a time to be able to get rates of change of vectors. So we're going to get the velocity, then we're going to get the acceleration using the velocity. But this is the theory that goes behind this. Next is going to be an example that demonstrates how to use rotating and translating frames. So, okay, so let's move on with the example. So the example that we're going to study first is going to be this one. Imagine that I have a shaft. Now the shaft is going to be described as follows. There's a shaft, and on the end of the shaft there's, if you want to call it, a wheel. And this wheel rotates on the shaft. So the shaft itself actually is rotating relative to the ground. And the angular velocity of the shaft is about the vertical direction. I'm going to call this point here, I'm going to call that point O. So O is at the one end of the shaft. I'm going to call this point at the other end of the shaft, I'm going to call it Q. And then there's a point on the circumference of the wheel, which I'm going to call P. And the radius of this wheel, I'm going to denote it by capital R. And then I'm going to denote the angle formed by the vertical direction with the direction QP. I'm going to call that angle theta. So what we have in this problem, you can see, is that we have a rotation and a translation, right? Because point Q is moving relative to point O because this horizontal shaft is moving in a circular fashion. And then the disk is also rotating. So the center of the disk located at point Q is such that point P is moving in a circle around point Q. And what we want is, or I should say the objective, is to determine the velocity and acceleration of P as viewed by an observer fixed to the ground. Now, in order to be able to do this problem, we have to decompose motion into different parts. And those parts are going to be to first figure out what's going on with Q, and then to figure out what's going on with P relative to Q. So you can see that Q, again, we're going to have to deal with different reference frames. So how many rotations do we have in this problem? We have 2 rotations. So we're going to need 3 reference frames. What are those frames? The first frame is going to be the ground. which is going to be our base reference frame. So the base reference frame is going to be the ground, which I'm going to label as G. And then the first rotation is going to be defined by a reference frame, which is going to be the shaft. And the second rotation is going to be defined by, I'll call this S, and then it's going to be defined by the disk, because the disk rotates relative to the shaft. So let's figure out how we're going to lay down all the coordinate systems in these different frames. So G is going to equal the ground, and that is our base reference frame. Now, a coordinate system fixed to the ground, the origin is going to be at O, because O is fixed to the ground. I'm going to put the direction big EX to be along omega. And that, again, it's the same thing that I've done in other problems, where the angle theta is defined from that direction omega, which is upward. So in order to preserve a standard cylindrical coordinate system, I'm going to put EX along omega. I'm going to put EY to be along OQ, and then EZ is going to along OQ when t equals 0. So at t equals 0, frozen at t equals 0 is going to be the direction EY, and then EZ is going to be equal to EX crossed with EY. Now it's important that it's not OQ, because OQ is actually fixed to the shaft, but OQ when t equals 0 is whatever direction OQ happens to point at time t equals 0, and that's fixed to the ground. So the next frame is going to equal the shaft, and now I'm going to put the origin of this reference frame, of the coordinate system fixed in this reference frame. I'm going to put it at point O, because point O is also fixed to the shaft. And then I'm going to label EX to be the same thing as big EX, which is along omega. I'm going to label EY to be along OQ. Notice it's not OQ when t equals 0, it's actually OQ, because that direction is fixed to the shaft. And then EZ is going to equal EX crossed with EY. And then the third reference frame, which I can put right on this page here, I'm going to call this the disk. That's what I labeled it. And then I'm going to put the origin of this coordinate system that's fixed to the disk at point Q. Because notice that Q is fixed to the disk. It also happens to be fixed to the shaft, but it's fixed to the disk. And I'm going to put U sub R along QP. I'm going to put UZ is going to equal EZ, and then U sub theta is going to equal UZ crossed with U sub R. So now let's look at this picture. Here's the direction little ex, and here's the direction little ey. Those are both fixed in the shaft. So ex, ey, ez. If I take ex crossed with ey, I get ez, ez's into the page. So this basis, ex, ey, ez, is fixed in S. The next coordinate system is this coordinate system that is fixed to the disk. So I've got the direction U sub R, I've got this direction U sub theta, and then notice UR crossed with U theta is equal to UZ, which is also equal to EZ, and there's an angle theta that's defined here, and the basis UR, U theta, UZ is fixed in the disk. So just like the theory that we just got through describing, you can see now that what we have is that the position of point P relative to O, because remember I need to measure from a point that's fixed in the ground, and O is fixed in the ground, is equal to the position of Q relative to O plus the position of P relative to Q. Now, let's suppose that I label the distance from O to Q, just to make this complete. I'm going to call that distance L. Okay? Then you can see that the position of Q relative to O is equal to L times EY, and the position of P relative to Q is equal to R times UR, which gives me that the position of P relative to O is equal to LEY plus RUR. Now we're not going to combine anything here. We're going to keep these pieces separate. We're going to differentiate them separately, and we're going to put them together. We don't need to combine everything. We can actually keep these parts of the vector away from one another and differentiate them separately. So let's do that. So we know that the velocity of point Q, as viewed by an observer fixed to the ground, is equal to the rate of change in the ground of the position of Q relative to O. But the position of Q relative to O is expressed in a basis that's fixed in reference frame S. So this is d dt in S of the position of Q relative to O plus the angular velocity of S in G crossed with the position of Q relative to O. Now d dt in S of the position of Q relative to O is equal to 0 because L is constant and EY is fixed in S. The angular velocity of the shaft as viewed by an observer fixed to the ground is equal to omega, which is equal to omega EX, the way I defined EX. So therefore, the angular velocity of S in G crossed with the position of Q relative to O is equal to omega EX plus LEY, crossed with LEY, which is equal to L omega EZ. So therefore, the velocity of point Q as viewed by an observer fixed to the ground is equal to L omega EZ. So that gives me the first part. The next part is going to be the velocity of point P, and this is now going to be the velocity of point P as viewed by an observer fixed to the ground is equal to the rate of change in the, if you go back over here, it's the velocity of P, and I've got this relative to Q, right? So the velocity of P, and this is going to be d dt and G of RP relative to Q, right? And this is going to equal d dt, and now this frame is d because the position of P relative to Q is going to equal the is expressed in a basis that's fixed in reference frame D. So this is d dt and D of the position of P relative to Q plus the angular velocity of D and G crossed with the position of P relative to Q. Now d dt and D of the position of P relative to Q is equal to 0, because if you look back at the position of P relative to Q, it's expressed in a coordinate system that's fixed in the disk. The angular velocity of the disk as viewed by an observer fixed to the ground is going to equal the angular velocity of the shaft as viewed by an observer fixed to the ground plus the angular velocity of the disk as viewed by an observer fixed to the shaft. The angular velocity of the shaft as viewed by an observer fixed to the ground we already have. So we need now the angular velocity of the disk as viewed by an observer fixed to the shaft, and that's equal to theta dot times uz. If we go back over here to our picture, you see that uz is the direction normal to that plane, and so we get theta dot uz, which gives us that the angular velocity of the disk as viewed by an observer fixed to the ground is equal to omega ex plus theta dot times uz. But again, we need to decompose ux or ex into the basis ur u theta uz, and you can see again that it's equal to cosine theta times ur minus the sine of theta times u sub theta, which gives us that the angular velocity of the disk as viewed by an observer fixed to the ground is equal to omega cosine theta ur minus omega sine theta u sub theta plus theta dot uz, which then gives us that the angular velocity of the disk as viewed by an observer fixed to the ground crossed with the position of p relative to q is equal to omega cosine theta ur minus omega sine theta u theta plus theta dot uz crossed with rur, which is equal to, now I've got u theta crossed with ur and uz crossed with ur, which gives me r theta dot u theta plus r omega sine theta times u z, which tells me that the velocity of point P as viewed by an observer fixed to the ground relative to point Q is equal to, now let's look at this. This is equal to, the first term in the transport theorem is 0, so the only thing that's left is the second term in the transport theorem, which gives me r theta dot u theta plus r omega sine theta times u z. So therefore, we obtain the following result, which is that the velocity of point P is viewed by an observer fixed to the ground, which is equal to the velocity of point Q as viewed by an observer fixed to the ground plus the velocity of P relative to Q as viewed by an observer fixed to the ground is equal to, well, let's grab the velocity of point Q. That's equal to L omega Ez plus r theta dot u sub theta plus r omega sine theta times u z. Now, you'll notice that I have these two pieces expressed in two different bases. The first part is expressed in a basis fixed in reference frame S. The second part is expressed in a basis fixed in reference frame D. There's nothing wrong with that, because each piece of this vector is more conveniently expressed in bases fixed in different reference frames, which is exactly what I got through describing at the beginning when we were doing the theory. So we're just going to keep these pieces separate as we go through and do the acceleration. So next, what is the acceleration of point P as viewed by an observer fixed to the ground? Well, it's equal to the rate of change as viewed by an observer fixed to the ground of the velocity of Q as viewed by an observer fixed to the ground plus the velocity of P relative to Q as viewed by an observer fixed to the ground. And that is the acceleration of Q as viewed by an observer fixed to the ground plus the acceleration of P relative to Q as viewed by an observer fixed to the ground. But in order to compute each one of these pieces, we can do them without regard to the other piece. The acceleration of Q as viewed by an observer fixed to the ground is going to equal d dt in g of the velocity of Q as viewed by an observer fixed to the ground. That's what we just got through saying. We just wrote it down up above. But that, because that velocity is expressed in coordinates that are fixed in reference frame S, this is equal to d dt in S of the velocity of point Q as viewed by an observer fixed to the ground plus the angular velocity of S in G crossed with the velocity of point Q as viewed by an observer fixed to the ground. That applies because the transport theorem needs to be performed from S to G, because the vector VQG is expressed in coordinates fixed in the shaft. So what is d dt in s of the velocity of q in g? Well, if you go back to the velocity of q in g, you'll see that it's equal to L omega Ez. But I didn't say that omega was constant, so this is L omega dot Ez. The angular velocity of the shaft as viewed by an observer fixed to the ground crossed with the velocity of point Q as viewed by an observer fixed to the ground is equal to omega Ex, because remember that's the angular velocity, crossed with this velocity of point Q as viewed by an observer fixed to the ground, which is L omega Ez, which is equal to minus L omega squared Ey, because Ex cross Ez is equal to negative Ey. So that tells me that the acceleration of point P as viewed by an observer fixed to the ground, the acceleration of point Q as viewed by an observer fixed to the ground is equal to minus L omega squared Ey plus L omega dot Ez. And that just comes straight from the fact that we're dealing with a system where the first part of the transport theorem led us to that result. So if you go all the way back to the beginning, you'll see that the angular velocity of the shaft as viewed by an observer fixed to the ground crossed with the position of Q relative to O was the only term in the transport theorem that survived. And so as a result, it's the only term that winds up contributing in that rate of change that I see in this part of the acceleration. So the second part of the acceleration is going to be the acceleration of P relative to Q as viewed by an observer fixed to the ground. Well, that's equal to, as we did before, d dt in g of the velocity of P relative to Q in g. But the velocity of P relative to Q in g is expressed in coordinates that are fixed in d. So this is equal to d dt in d of the velocity of P relative to Q in g plus omega dg crossed with the velocity of P relative to Q in g. So now let's take the rate of change in reference frame D of the velocity of P relative to Q in g. What's that equal to? Well, in order to do that, I have to go back to the expression for the velocity of P relative to Q in g, and it's equal to r theta dot u theta plus r omega sine theta uz. So this gives me r theta double dot times u sub theta, and then I get plus r times omega dot sine theta plus omega theta dot cosine theta times u z. And that takes care of that first term in the transport theorem. And then I've got the angular velocity of d in g crossed with the velocity of P relative to Q in g, which is equal to, now let's go back over here and grab this angular velocity. The angular velocity was omega cosine theta ur minus omega sine theta u theta plus theta dot uz. So I got omega cosine theta ur minus omega sine theta times u theta plus theta dot uz crossed with r theta dot u theta and then plus r omega sine theta uz, which is equal to, so ur crossed with u theta is uz, so I get r omega theta dot cosine theta times uz. Ur crossed with uz is equal to minus u theta, so I get minus r omega squared cosine theta sine theta times u sub theta, and then u theta crossed with u theta is 0, u theta crossed with uz is ur, so I get minus r omega squared sine squared theta times ur, and then the last term is uz crossed with ur, which gives me minus r theta dot squared times ur. So therefore, the acceleration of p relative to q in g is equal to, let's gather up the terms here. I've got minus r theta dot squared plus r omega squared sine squared theta times ur. That gives me that term. And then you'll see that in the u theta direction, I've got a minus r omega squared cosine theta u theta and an r theta double dot. So I got plus r theta double dot minus r omega squared cosine theta times the sine of theta times u sub theta. And then I've got plus, now I've got the uz terms. I've got r omega theta dot cosine theta and another r omega theta dot cosine theta. So I've got 2r omega theta dot cosine theta, and then I've got plus r omega dot sine theta times u z. So that's the second part of the acceleration. So combining the acceleration of q in g with the acceleration of p relative to q in g gives the following result. That the acceleration of p in g is equal to the acceleration of q in g plus the acceleration of p relative to q in g, which is equal to, let's go back to the acceleration of q in g, minus L omega squared EY plus L omega dot EZ, and then I've got plus all these terms, which actually the first term is actually negative, so it's minus R theta dot squared, and then plus r omega squared sine squared theta ur, and then I've got plus, I've got r theta double dot minus r omega squared cosine theta sine theta times u sub theta, and I've got plus 2r omega theta dot times the cosine of theta, and I've got plus r omega dot times the sine of theta. And that's times u z. And you can actually see that this acceleration is broken up into two parts. You can see that the first part, which is the acceleration of q and g, is expressed in a different basis from the acceleration of p relative to q and g. The acceleration of q and g is expressed in the basis that is fixed in the shaft because the position of q relative to O is expressed most conveniently using a basis that's fixed in the shaft, whereas the acceleration of p relative to q and g is actually expressed most conveniently in a basis fixed to the disk because the vector from q to p, which is the position of p relative to q, is most conveniently expressed in the basis ur u theta uz, which is fixed to the disk. So that's consistent with the geometry of the problem, which is that the shaft is rotating in a circle horizontally, if you want to think of it that way, of radius L, and the disk is rotating about an axis orthogonal to the plane of the disk with an angular rate theta dot. And as a result of those two, so the shaft is, the point Q is moving in a circle, and the point P is moving in a circle relative to Q. So Q is moving in a circle relative to O, and P is moving in a circle relative to Q. And that's what's reflected by these different parts of the acceleration. So this example provides a way to be able to sort of deconstruct a vector into its constituent pieces, where each piece of the vector, the rates of change of that point, can be computed using the most convenient basis in whatever the most convenient reference frame is, and then you can just combine the results, which is what I did in this lecture. So that's going to be the end of this lecture, and we'll move on to other topics later on.